Okay, in the last video we looked at covalent bonds. We're looking at these examples on the bottom, so we'll take a look at these ones. Nitrogen is a group 5, so it needs 6, 7, 8, needs 3 more to get an octet, and each hydrogen needs 1. So you can see here nitrogen needs 3, so it shares 3. Shares 3 to get 3. So if we take a look here, nitrogen 1, 2, 3, 4, 5 signified by the red dots. Hydrogens signified by the blue X's, so you can see here nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Each hydrogen has 2. And of course you can see these diagrams, how cluttered they get when we use dots. So I circled the shared pairs there, and of course we exchange that for a line, which means a shared pair. Carbon is a group 4, so it needs 4 more, so share 4 to get 4. And you can see, yeah, this one gets really cluttered here. So the red dots signify what carbon has, so on each side here. And then hydrogen, X, 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 X. So you can see carbon has 2, 4, 6, 8. Each hydrogen has 2. The circled pair is represented by a line, and that's how we can make that structure formula here. So you can see these look a lot neater than the dot formulas, where they tend to get cluttered, especially when we have like 5 atoms here. All right. Looking at this example here, given the Lewis symbol for nitrogen and fluorine, predict the formula of the stable binary compound, a compound composed of 2 elements only, formed when nitrogen reacts with fluorine and draw its structure. So if you look here, the Lewis symbols for nitrogen and fluorine reveal that, of course, nitrogen is group 5, so it has 5 electrons. Fluorine is group 7, so it has 7 electrons. So we need to find a combination of 2 elements that result in an octet of electrons around each atom. Nitrogen requires 3 additional electrons to complete the octet. Fluorine requires 1. Sharing a pair of electrons between nitrogen and fluorine will result in an octet for fluorine, but not for nitrogen. We therefore need to figure out a way to get more electrons for the nitrogen atom. So if we just go 1 to 1, yeah, fluorine gets an octet, but nitrogen doesn't. But nitrogen must share a pair of electrons with 3 fluorine atoms to complete its octet. Thus, the binary compound between these elements would be NF4, nitrogen trifluoride. Okay, because that would make it work. So if we take a look here, 1 nitrogen, 3 fluorides. So yeah, if you look at the cluttered dot diagram here, nitrogen's it needs 3, so it shares 3. So shares 3 to get 3. So we'll have a fluorine attached to the left, bottom, and right. So you can see that's what we have happening there. A fluorine share pair right here, share pair here, share pair here. And of course, if I cover this up, take a look at what happens. If I cover up the fluorine part and just look at the shared pairs here, nitrogen has 8. If I look over here, fluorine has 8. Over here, fluorine has 8. Over here, fluorine has 8. Okay, so the shared pairs exist with one atom part of the time and another atom the other part of the time. And of course, to avoid the clutter here, wherever there's a shared pair, use a line to represent that. Then you can see, yes, that looks much neater. And of course, any pairs that aren't shared, you just simply draw as dots. So nitrogen trifluoride, that's what it would look like. Looking at the next page here, the Lewis structure in the center shows that each atom is surrounded by an octet of electrons. Once you are accustomed to thinking that each line represents 2 electrons, a shared pair, you can just as easily use the structure on the right to form the octet. So that's just reinforcing the idea that, yes, these 2 diagrams are equivalent. A line representing a shared pair makes the diagram look a little neater. Okay. Compare practice exercise. Compare the Lewis symbol for neon with the Lewis structure for methane. In what important way are the electron arrangements about neon and carbon alike, and in what way are they different? So methane we had earlier, I believe. There's methane right there. Okay. So if I'm looking at neon and methane, of course neon is just well, we just represent the symbol with 8 electrons around it. So it has a full octet. Each of these lines represents a shared pair. So if I look at what carbon would have, 2, 4, 6, 8. It has an octet as well. So both atoms have octet electrons. However, the electrons about neon are all unshared, whereas carbon, all of its electrons, all 4 of them, are shared with hydrogens. So the shared pair with carbon some of the time, and with hydrogen other times. Okay, lastly, so look, we have single bonds. We could also have multiple bonds, depending upon what we need to do to get an octet. A shared electron pair constitutes a single bond, generally referred to as a single bond. In many molecules, atoms attain a complete octet by sharing more than one pair of electrons. When two electron pairs are shared, two lines are drawn in the Lewis structure representing double bonds. In a carbon dioxide, for example, bonding occurs between carbon with 4 valence electrons and oxygen with 6. So we take a look at this scenario, carbon and oxygen. CO2 has 1 carbon, 2 oxygen, so you can see how this works. Carbon needs to gain 4, so it must need to share 4. 2 with each. And the reason why it's 2 with each, because each oxygen is a group 6. 6 plus 2 is 8, it needs 2 more, so it'll share 2. So you can see here the 2 electrons here from oxygen, and if I could put 2 on one side here for carbon, we have a 2 shared pairs here, and also 2 shared pairs here. Since one shared pair is signified by a line, we would draw 2 lines here, indicating that in total there's 2 plus 2 is 4 electrons here, and 2 plus 2 is 4 electrons here. So if I take a look, this oxygen would have 2, 4, 6, 8. This oxygen would have 2, 4, 6, 8. And the carbon, each line represents 2 electrons, 2, 4, 6, 8. So you can see it all works out there. Every atom has an octet of electrons. As the diagram shows, each oxygen atom acquires an octet by sharing 2 electron pairs with carbon. Carbon acquires an octet by sharing 2 electron pairs with each of the 2 oxygen atoms. Each double bond involves 4 electrons. Okay, we could have triple bonds too. Of course, now, I know I mentioned before that we don't usually put 3 electrons on the side, but when we're forming bonds, sometimes we have to do that. A triple bond corresponds to the sharing of 3 pairs of electrons, such as in the N2 molecule. So it is drawn like this here, but we could have easily have drawn it like this, and we have their lone pairs of electrons, and we could show like this way if you like, even though it kind of violates that rule of, we can only have 2 electrons per side. When we're bonding, sometimes we need to. So nitrogen's a group 5, 6, 7, 8. It needs 3 more electrons, so share 3 to get 3. So each shared pair here, of course, shared pair, shared pair, shared pair, can be represented as a line, so we can see we have a triple bond there between the nitrogens. Okay? Because each nitrogen atom has 5 electrons, 3 electron pairs must be shared, etc., etc. The properties of N2 are in complete accord with Lewis structures. Nitrogen is a diatomic gas, so it's one of the Hofbrinkels with exceptionally low reactivity that results from the very stable arrangement. The nitrogen atoms are separated by only 1.10 angstrom. Now, angstrom is a unit of length. If you just make this little note here, it's a Swedish word actually, 1 angstrom, and it has a little circle over the A. I'm not sure why. It has to do something with the Swedish language, I suppose. Equals 10 to the negative 10 meters. So here we're talking about really small distances, of course. And we're going to be looking at what is the relative distance between atoms when we have different bonds. The short separation distance between 2 N atoms is a result of a triple bond between the atoms. From studies of the structures of many different substances in which nitrogen atoms share 1 or 2 electron pairs, we've learned that the average distance between bonded nitrogen atoms varies with the number of shared electron pairs. If you look at this. Now I think I'll stop the video there, and the third video will bring it home and look at the final part.